All right. Welcome everyone to module 7.3 on tissue folding. Cheers to still being here on day 7 of the workshop. I'm Priyom. I am a postdoc at Duke, but years ago now, I was a graduate student with James, and I worked closely with Julio, who taught me a lot about the Focal Point Plasticity plugin, which we'll be using a lot again in this module. So uh, what I want to do is first sort of like jump into what we will be talking about today. And sort of the motivation is that we as biological organisms, come in a variety of shapes and sizes. But all of us began from, say, a clump of cells, which got molded and structured into the tissues and organs. So to think about from a modeling perspective, so we're basically trying to understand how we can basically model a flat group of cells into something that becomes folded over time. And so we will be using the focal point plasticity plugin to achieve this, so that we can model our cells. So I have a comment that they are not seeing the screen sharing. Is that true
Uh,
for everyone?
The screen
Priyam,
share
it's
is fine.
fine.
Just
Maisha,
ignore.
you may need to click Priyam's screen at the top bar. You're in the wrong tab.
Okay, awesome. Thank you, Aiden. Okay, so what we're going to be doing today is using the focal point plasticity plugin. We're going to incorporate it between cell pairs and modifying these properties. We're going to model cell behaviors like bending and epithelium, and eventually use these properties to get them to pinch off, like forming a segment. And this is the overview. I will be coming back to it a couple of times. It might so happen that the biological objectives are not what you're interested in. And that's completely fine. So what I will do is, as we go along, I will also make sure that I'm talking about some of the specific CompuCell capabilities that I'm using if they're more useful for some of the other tasks you're interested in. Okay, so jumping back a bit to the biology, just want to stress on how basically changing shapes during development is such an integral part. For example, all of us vertebrates have the structure called the neural plate, which during development will hinge and basically form this folded tube, and that's eventually going to, form your brain and your spinal cord. These examples of where you actually have a flat sheet of tissue into basically folding into a tube also occurs across gastrulation. So, for example, for example, you have examples in fruit flies where the ventral side of these cells, marked by these yellow regions over here, during gastrulation, they're going to constrict, invaginate, and this is one way of bringing these external cell layer inside the body of the organism so that it can later on build tissues and organs. And so these examples are so, like, very, very common across different organisms, including C. elegans, and then they're integral to basically building up a growing organism. But now if we like look at these pictures and sort of try to ask the question, so why, what are sort of the processes that are responsible for generating these shapes? And to think about it, you have to take a step back and think about the cellular behaviors itself, and the role of something called the cytoskeleton, because there are, proteins, for example, like myosin and actin, that together can play a role in processes like apical constriction. So, for example, what happens during this process is that myosin is going to get accumulated at the top of the cell towards the apical regions. And these motor proteins are going to pull on the actin network around that cell, which is eventually going to sort of like reduce the apical surface area, giving the cell a very wedge like shape. And, you know, on the scale of like one cell, you might not be able to see a difference. But when groups of cells together are able to like, do a collective effort of reducing this apical area, you're going to see this like invagination or this shape. There are also documented cases of multiple other processes working with apical constriction to give tissues a folded shape. For example, you could couple it with cell extrusion, apoptosis, or you could also have cells actually changing their shape to adopt a more shortened cell. And this will also induce folds and folds in the tissue. But at the core of all of this, it lies that you have cellular processes that's actively bringing a change into sort of the tissue morphologies. And so now, taking this example from biology, we're going to translate it into a modeling scenario where, because we know that so myosin motors are responsible for pulling in and reducing the apical surfaces of these cells, um, we can now model this as springs using our focal point plasticity between compartments that basically mimic pulling forces and being able to sort of like invaginate our tissue. So basically, this is the architecture that we're going to be following for this module. So for our first case, and I'll talk a little bit about our first task in a second. So we're going to start by building an epithelial layer comprising of three compartments: apical, lateral, basal, which is sitting on top of an ECM layer. And we're going to add focal point plasticity links between the apical regions. In our second scenario, we are going to change the FPP properties so that we see a bend in the epithelial layer. And for the next three exercises, what we're going to do is try to have a little bit more control on the focal point plasticity plugin. So we're mostly going to be working in the steppable function. Um, and what we're going to try to change focal point plasticity plugin properties in space and time. In the next exercise, we're going to be playing around with breaking some of the FPP links and sort of being able to visualize where we have broken those links. So for our starting module, so Julia has done such a fantastic job of already like walking you through all of the focal point plasticity plugin capabilities already, and you have already seen sort of a simulation like this in his 5.1 module. So this is where we're going to begin. So our goal is the following. So we will begin with these three compartments, basal, lateral, apical. They're sitting on top of this ECM layer. And our goal is to sort of mimic a cell body like this, where you have, proteins like integrins on the basal side, which is going to communicate with the ECM over here. On the surface of the cell, you have like a bunch of other adhesion and tight junctions. That's basically, connecting the intermediate filaments across different types of cells. As you keep going towards the apical side, you have a bunch of different structures that's going to communicate with the, external environment. So to basically mimic something like this, we're going to break down our cell body into different compartments, and that's what we're going to do. So I thought that since you have already seen a lot of these capabilities, maybe I can take a break here, about 5 to 10 minutes, depending on how we do, and maybe you can try to build on the simulation yourself. Um, so I have sort of the steps for it for this particular module, where I've listed down basically what are the things we need to do. Obviously, you might run into some other challenges. So yeah, I'll keep monitoring the chat, but maybe we could try building the simulation. See if you have are able to start on the incorporate all of these components correctly. In the next couple of my slides following this, I also have step-by-step instructions. So if you prefer that, feel free to check those out as well. If you prefer not to build this from scratch, The code for this should be available in module 7_3_1 in the demo folder. So I'll just restate our goal. So what we're doing is we're going to create a simulation. We're going to place our epithelial cells comprising of three compartments, basal, lateral, and apical, and they'll be sitting on top of the ECM layer. And yeah, as you have seen versions of this code, so feel free to download the code, or if you're doing it from scratch, these are the steps that you'll be incorporating. Yeah, so I'll be monitoring the chat. If you have any questions or any outputs to share, please let me know. And hopefully the task is clear on what we're trying to do. If not, please let me know, and I'm happy to talk again. So there's a question from Eritrea regarding that apart from FPP, we should also have contact. Yes, absolutely. So make sure that you have both contact and contact internal selected. Oh, that looks interesting. So yeah, I think you have got most of the parts right. I think the only thing is depending on what initial size of the ECM you have set. Because if you specify the size of the ECM with 35 as being the width, you might not have put the appropriate volume. So that's why the ECM cells look much more smaller. But apart from that, a lot of things look good. I think there are some cluster reinitialization that you might have to do as well, which we will get to in a second. Yeah, that looks greater. So so sort of, yeah, these are and I think that's the beauty of like doing the simulations. As you do them, you will realize what sort of like pieces are missing so that you can put them back. So let me just walk you through these steps, unless I hear that somebody and that you all want some more time to try the simulation. Otherwise, I'm going to just walk through some of these steps, and maybe we can discuss them as we go along. So the starting simulation for these sort of steps. Oh, I'm so sorry. The starting steps you have already seen so far. So our first task was to, setting up our X and Y dimensions, which you have already, seen across using threaded. So I've set the X dimension to be 350 and the Y dimension to be 100. And just putting in periodic boundary conditions on the X axis. Um, you can also avoid doing this step and put no flux as well. But for now, I've set them to periodic. Our next step, initializing our four different cell types. So we have apical, lateral, basal, and ECM. And then we are adding our our plugins, obviously. So we have contact internal, we have our focal point plasticity, and we have our volume plex, which should already be selected. So you should also have center of mass and cell neighbors already selected as well. Yeah, Aritra, that looks great. The ECM cell volumes look very correct. And then in the chemical fields, what we can do is like largely ignore them because we don't have any fields to initialize. Our final step, as it brings us to the contact energy, we will be talking about the energies a bit more in a second. Let's just make sure to remember to put the neighbor order to 4, which you can also edit in the XML file, but yeah, I'm just setting them to 4. Okay, so with these steps, you should have a basic simulation. So even now, if you take, if you pause, hit maybe just step, you should be able to see a simulation where your uniform initializer is going to fill your simulation region with all of these 4 different cell types. So this is where we need to make our first couple of adjustments because this does not have the structure of the epithelium that we want. So going back, remember that our epithelium structure that we were trying to mimic was sort of this, where we have ECM, basal, lateral, and apical compartments facing each, one after the other. And so now what we can do here is that this block of code that allows us to specify our cell types, we can make sure to have, separated into 4 cell types so that we can, start building our columns. So in the next step, what we're essentially doing is starting by first building our ECM layer. So I've set the ECM layer to be slightly bigger than the rest of the cell. So you can see that it's a little bit more taller. So the positions that I've chosen here is that the ECM height goes from 0 to 35. And this block of code under the region only has 1 cell type. So that's how we're controlling um, width, the width and the height parameters of this particular cell layer. So the next step then we're going to do is we're going to put our basal layer on top of the ECM, and we are going to the cell size that I picked up here is 7, but you could you could play around with cell size as a parameter, and you could have different heights and widths of your cells that you want. So the next cell layer that I'm placing here is the basal layer, and then we're going to go to the next step, which is we're going to place the lateral layer on top of the basal layer. So what you can see here is that the height parameter across all of this is the one that's changing. And once you have placed that lateral layer, you can now finally put in your apical layer over here. I don't know if this makes sense. I mean, the parameters are yours to play with. These are some dimensions that, you can choose based on the size of the simulation. But that's how we're placing the cells on top of each other. Okay, so once we have performed these steps, what we're going to do is make sure the target volume of the ECM layer is set up correctly. So we're going to set it up to whatever 35 times 7 is, which is 1225. And hopefully this now should reflect upon on your simulation, where we should have, if you sort of like run this simulation right now, you should be able to see the ECM layer, and you should be able to see all your basal, lateral, and your apical cell layers. Do these steps make sense so far? Are there any sort of like questions on the? Okay, thank you. That's great. So from just making these sort of so we have a question in the chat. Is the ECM supposed to be at the top? So depends on how you define the top and the bottom. So I've oriented the simulation so that this is the ECM layer at the bottom is mimicking the substrate, and the apical layer is like opposite it. If you want your simulation to be flipped upside down, feel free to sort of arrange it that way. So if you look at the pixel markings, this is how this is how the y-axis is oriented. So 0 is over here. So when you do 0 to 35, the pixels from 0 to 35 are going to be filled with these there, if that makes sense. And so what now, if you're like, if you sort of like look at the simulation, what you should be able to see is that we have like links all over the place. And so our next goal here is sort of to be able to remove, um, some of these focal point plasticity links that we don't want. And so if you actually go to your XML code, I just want to quickly recap what focal point plasticity tags are going to look like. So each focal point plasticity tag is going to be between two cell types, which is like type 1 and type 2. In this case, I'm giving you an example of both, cell types to be the same, but they could be across, all multiple different cell types. Inside these tags, you're going to see multiple, components of the plugin. So the first one, which is lambda, it's basically going to tell you how strong your FPP link is. The second one, which is activation energy, this is a component that's added to the energy function, if you remember from Pedro's lessons last week. So basically, this is sort of adding an extra term to the energy function to make the link creation a bit more favorable. And then you have parameters like target distance, which is basically what you're trying to achieve. So that sets out what the target distance between your two compartments should be. This also has a feature of maximum distance. So for example, if you have a link that exceeds beyond this maximum distance, that link is going to, disappear. And then you have also the option of creating, junctions. So basically, how many links you should have per cell, and that's being set up by this max number of junction parameter over here. So given that these are our tags, let's go back to our entire focal point plasticity plugin code. And what we're going to do is we're going to remove all of our other tags. And for this simulation, we're only going to keep our links between the apical compartments. You can also try keeping some of these other links and seeing what happens. But as the goal of this module becomes more clearer, you will see that keeping the links between the apical compartments will help you achieve this better. So we're only keeping the apical links here. And also, you have seen this probably by now. So don't forget to uncomment the local tag because that will allow you to make changes in the steppable function in a bit. So if you have these steps done, then you should just end up with something like this, right? So you have the local uncommented, you only have tags between the apical compartments remaining, and you have sort of these, FPP parameters. So if you were to also run your simulation at this step, this is what you would see. You'd see sort of like these white lines representing the links, but they would be placed randomly because in our simulation, if you just sort of like set the maximum number of junctions to just one, so cells are randomly trying to grab onto just one sort of neighbor, and then that's why you don't have links between all of these pairs. But that's not going to matter because our next step is we want to make a lot of these changes in the steppable itself that allows us better control on the timing of putting the links in and sort of being able to manipulate their properties. We have seen these examples in the previous modules as well. So we can set all of these focal point plasticity parameters to be 0. You can keep the activation energy in because we're not going to mess around with this parameter. So this is what your simulation should look like. If you set all of these variables to 0, the links in your simulation should just disappear. So now we have one final step remaining in the XML file, which is we have to just adjust our contact energies. And then while, like when you're doing this process, think back to the picture of the epithelial cell. where you have, sort of like a very specialized structure to the cell with sort of basal at the bottom close to the ECM, the lateral on top, and then you have the apical compartment. So, right, so there's a question, what is the target volume for the ECM supposed to be? So that's, you can set it to 1, 2 to 5. And I believe that's because it's, right. So, hopefully these steps make sense so far. Let's see if there are more questions. So the comment is, if I do that, the ECM expands into the other cells and destroys them. So is it just this destroying other ECM, or is it actually invading into the cells? So the ECM contact energy, we're going to set it so that basically, the ECM cells are mostly disintegrated and mixing with each other. That's like our version of creating, because ECM is not quite the epithelial like cell type. So you can try to create a more continuous material. One other version is that you don't even break down DCM into different cells. But I think once you fix the contact energies along with setting the volume, I think you should get the right simulation. So yeah, let me know in the comment if your ECM is destroying other cells as well, or is it just other ECM cells? If it's just expanding into the other ECM, that's totally fine, because we're trying to sort of like mimic it being more like a continuous material in this case. All right. So what we're going to do now is sort of try to set up first our internal contact energies. And the rule that we're going to follow for the internal contact energies is that we want our cells to roughly stay together. We don't want them to sort of like hate each other too much. So we're going to, set low values for these interacting components. The rest of these, for internal contact energies, they are not going to matter as much. So we can set them to 0. But yeah, these apical to lateral, apical to basal, or basal to apical, we're just going to set to like low value so that the cell itself is like holding shape. If you want to see some of the values that I have picked, so this is these are some of the values that I've set. So all the internal contact energies across pairs, so apical to lateral or lateral to basal, or where is apical to base, apical and basal, I've set them to 2. And then for our final pairs of contact energies, so now we have to be a little bit more careful. So now if you imagine the structure of our epithelium again, so you saw that ECM was facing away from the apical side and whatever the apical side is communicating with, which in this case we're calling medium, but could be sort of like in, some sort of like fluid or whatever environment these cells are placed in. So anytime you see ECM communicating with something like the apical or medium side, we want to set those contact energies to be super high so that these cells to prefer not to interact with these cell types. Similarly, that works for the medium to basal. You want to set them high so that the basal do not try to communicate with this with the medium. Across the other components, so for example, the lateral or the apical lateral across cells, you can set them to be fairly high-ish, whereas as these cells are interacting with each other, you want the apical-apical surfaces of neighboring cells to be roughly touching, similar for lateral cells to be roughly touching, or basal cells to be roughly touching. So you want to set them to on the more lower side. And I've set these values to be slightly higher than the internal contact energies themselves. So these are the value chart that I have, where these lowest values I've set them to be 5. So between medium and apical, this is 5. Between apical and apical, this is 5. As you go towards the highest values, for example, between medium and ECM, you can go as high as 20. So these are some of the values that I've picked out. I mean, there's obviously a lot of different combinations. So yeah, feel free to play around with with those as well. But hopefully, ultimately, and you have seen examples in the chat already. So once you have implemented these steps, you should be able to get something like this. So at this point, what we have are 4 different cell types. We are roughly in their, correct volumes through the XML. We have deleted all the FPP links, but we still, if at this point we were to apply any additional links through the XML, through the steppable, we'll still have this problem that the our cells still don't know that they're part of a common cluster. And this is something you have heard from Julia as well, that we need to make sure that these compartments are, reinitialized as part of a larger cell group, so that when you apply forces on one, you're able to sort of, um, uh, evoke a collective response in the entire, like, sort of cell body itself. So that's what we're going to do now, as we move on to the steppable file now. So if you go to your edit leftmost side, you should be able to see our steppable file. And this is where we're going to make 2 changes. The first change we're going to make in the start function. But I'm going to stop here and quickly check in if the steps make sense so far. If you'd like me to repeat anything, or if this is too easy for you that you want me to move on. Awesome. Thank you so much, guys. All right. So then the next change we are going to make is sort of go to the sort function, and we want to make sure that we want to make sure that these cell compartments know that they're part of the bigger cell cluster. And as you look at this code, I'm going to quickly check the chat. So that's very interesting. So I'm looking at a screenshot that basically the same expanding into the other cell types. I am very much curious why you might have this. Could you check your XML column positions and see if there are any initialization on, like, top of each other? That could be one possibility if you want to share your code in the screen, share your code in the chat. Um, because because I can see the red compartments which have almost disappeared. So that would be my best guess if they were not initialized correctly. But yeah, if you can share your code, your XML code, that would be great. Okay, so coming back to what our steppable file. So we're going to do a couple of steps here. So by now you probably know the command where you can visit all cells of a particular type. So if you go to CCD Python, if you go to visit, you should be able to sort of like loop across all of your cells. And for this, we're going to select the apical cell type here. And we're going to do two steps. We're going to see that if you have, if at the same position that you found an apical cell type, if there are other cells that exist at that same position, you reassign those cells to be part of the same subgroup. So we started off with the apical. We have the apical cluster ID right here, which is cell.clusterid. And anytime we would find either a lateral or a basal cell at the same position along the x-axis, we would reassign their IDs to have the same cluster ID as that apical cell. And this is where the benefit of putting them on the columns comes in. You can have obviously design your own scheme of trying to initialize them in this step. And in our like third example, we will see of being able to control this more from the steppable itself. But this is one way because now we knew that the cells were basically stacked only along the y-axis. This lets you reassign them. Okay, so hopefully this step makes sense. Let me get to two more steps before coming back to some of the comments on the chat. So then what our next goal is going to be, if we have been successfully able to reassign, now we are going to do one more step. So this is our first step and we have reinitialized. And then now if we have, now we're going to do the same step, but now we're going to try to initialize links between the apical compartments. So we're going to go loop over all the apical cells. Then we're going to check if they're connected to any of these, any other apical cells at this time. So we're going to use the cell neighbor function here. So what we've done here, we've again like visited all cells of the apical type, and then we're looping over all of its neighbors. Once we detect a neighbor, which is not a medium, which is what this line is doing, and then we have confirmed that the neighbor is an apical cell type, we are going to put an FPP link between those cells. And in this case, I have put this FPP link by going to CC3D Python, Focal Point Plasticity, Link Management, create FPP link. And this function should create an FPP link between a cell of your choice and the second cell, which we have picked to be neighbors. And then this is setting the lambda, which is the strength of that focal point plasticity plugin. This is basically the target distance that we want. Remember, our cells already have a width of 7. So right now we have just set it to be equivalent to the width of the cell. And then 200 is the maximum distance over which these links are going to hold. Okay, so just to recap, we went to the steppables file. We made sure our cells were reassigned within the same larger cell group. And then we are now trying to put back our FPP links, but this time we have, sort of control over these between the cell and its neighbor that we're setting up the link. So in this case, we have, chosen a particular condition that they must be in contact with each other to have a link. And that's what this particular loop is doing. So if you sort of like run module 7 underscore 3 underscore 1, you should be able to see the simulation. So as I check out the chat, will you let me know if you have made it this far or if anything is unclear that I could go over. So Leonardo has a simulation that looks correct. I would say make sure that you have set the reassigned cluster IDs to make sure that these cells are within the same subgroup, but the ECM and the rest of the initialization looks absolutely correct. And then I'm looking at Daniel's values, 35, 35, 42. to lateral. So this looks good to me. Let me amend the XML. Oh, I also have two more simulations from UDs, which looks great. You can see the FPP link, and also you have done sort of the next step from what it seems like. And Kyle, your simulation looks good as well. Nathaniel, if you go into your contact internal energies, and can you set up the apical to lateral, apical to basal, and lateral to basal at 2? So your internal contact energies are a little too high at this stage. So the cell does not want to stay together. But your external contact energies look great. So I think that is working okay. And your focal point plasticity parts also look great. So the only thing I can spot is the internal contact energy. Um, so if you can check that out. So I have one more output from Raghu, who has done the next step as well, and that looks great. Aritra, this, oh, that's interesting. Yeah, this looks great. I can't see the length, so I was the colors threw me off for a second. But if you have confirmed links between your yellow compartments, I think otherwise the cell shapes look great. It tells me that they have been reinitialized to be part of the cell cluster. Cool. So thank you so much for sharing the output. Okay, so what we're going to do now is sort of the next part, which some of you have already done, which is fantastic. So we have a basic epithelium set up right now. We have been able to put FPP links between the apical compartments, and so our next task is now that we have like something that's pretty flat and we want to induce folds or invaginations in this tissue. So, my question to you is, given what we have with FPP links, what would be the best way to be able to incorporate folds in the tissue? And specifically, like, what would you change about which plugin would you use, and what did you change about it to be able to induce these folds? So I have one answer that says introduce a strong link for cells that are maybe 5 cells apart. That's actually a very interesting idea. So you're thinking of some sort of like long range communication where a cell that's not adjacent to each other somehow communicating further away, and they're somehow pulling on each other more strongly than the rest. And I mean that is a very valid idea, and you have, I guess, filipodial like processes that are able to like communicate across longer distances, and that makes complete sense. But if we were to like think about this particular examples, because now our tissue is already in place, and if you imagine that there are, it's like a very intricate cytoskeletal network that's connecting these entire groups of cells. So there are, filaments that are at the membranes of each of these, they're passing through the membranes of each of these cells that are, making like a very connected tissue layer. So in that case, what would be the best way to be able to achieve this? Okay, so I'm going to tell you the answer, but maybe not give you all the comments till I have tried it out. So what we're going to do, so another answer is tiny apical volume and large basal volume. That is exactly right. But the question is, how do we achieve that tiny apical volume, and what are the properties that we can change within our simulation that is sort of like mimic that? You can obviously change those percentages by hand. as well. That would also be valid if you are, combining it with some sort of timing mechanisms of some. But what we will be doing this is using the Focal Point Plasticity plugin to make those changes. So these are the steps that I suggest that we can implement to be able to see folds in the tissue. And maybe once you've implemented these steps, you can tell me why this particular thing works. So for our next couple of steps, this is what we're going to do, and maybe I'll wait like maybe a minute or two to see if you just want to make these changes on your own. So we're going to pick a specific simulation time. So far we have been working in the start function. Now, because we need to incorporate time into the equation that we're making these changes as a function of time, we're now going to move on into the step function. You can pick a specific simulation time to make these changes. And I would say that maybe pick up the apical cells between these two positions and try changing the lambda distance for those particular cells that are placed between these two positions. And you can also correspondingly change their target distance to 3. So remember, earlier we were at 7, now we are going to 3, and we were at 10, and we're going to 70. So these are the changes that we're going to make in our steppable step function and we're going to see what happens then. Yeah, so UDs has a nice simulation. So the only thing, I'm not sure. I would say check the strength of the links on what you have said. I mean, this would be a good simulation to compare it to, and check the X limits over which you're changing your parameters. So the comment is I can't quite tell what it changed to modify lambda. Okay, all right. So let's quickly look at the steps together, and we can circle back if you still have the same problem. So to make these changes, we are going to follow the 3 steps that I was telling you about. So now we are in the step function territory. So we're picking a particular, time so that you can see the changes pre and post. That gives you a little bit of time to acclimate to the simulation, but you can choose to not have this as well. And then we're doing the same thing again, where we're visiting all cells of a particular type, which is apical. Then we're picking all these cells that lie within these positions. And so just as a reminder, if you want to access the cell positions, you can use cell.xcom. Similarly, if you want to access this position along the y-axis, that's ycom. So this lets you to find out where that cell's center of mass lies in your simulation space. So if your cell COM is between these two positions, let's start modifying some FPP properties. And to basically find all the cell pairs that are connected by FPP, we're going to go to CC3D Python. We're going to go to the Focal Point Plasticity module, and we're going to visit all the links attached to a particular cell, which is right here. So for link in self.getFPP links by cell, we'll basically visit all the links that each cell has made. And remember, we had already designed our simulation so that the links were only made between apical compartments, neighboring apical compartments. So now what we're going to do is the 2 other steps where we were changing both our lambda distance. So to do this, we again could go to CC3D Python, go to Focal Point Plasticity, and if you now try to access the link property lambda for that, you can set your lambda distance to be 70. That's what our new value is. And similarly, we can also go to the same step where we could go to CC3D Python. You could do focal point plasticity, and then you could go to the target distance, and we can set the target distance to 3. So I'm just going to hold the screen here if that, because this summarizes all the steps and the changes we have done in the step function. So we picked up a particular time, we picked up a particular region in space, and then we went to each cell, which was within this region, and then we asked it to find all the FPP links that it was connected to, and for each link pair that it found, we set it to we changed the values of the lambda distance and target distance. And this is how we could use the steppable file and the focal point plasticity features to be accessible within the steppable function. Does this make sense? Uh, Let me know if doing this changed your simulation. Does this help out with the simulation at all? Where now you were able to change your both your lambda distance and your target distance in this way. So give this a shot and see if you get a different output. So as you look at these outputs now, could you guess why we did the two things we did, and why the shape of the tissue sort of now looks different than what we started off with? Right. Manisha has an answer to the question. So we turn on the link strength in the neighboring regions, but only in the desired region. So this was what sort of like made the difference. Nathaniel, that looks great. That looks great. Um, and so this is basically the key, that to be able to generate a fold in a particular region, we have to induce some sort of asymmetries. And you have to change, some proportional property. So we were trying to mimic recruitment of myosin to these apical regions. And so we were mimicking them with our spring-like forces by sort of increasing our strength of our FPP links in those regions. And that's what we achieved by setting the lambda distance to be very large. And that, coupled with the fact that we set our target distance to be very small, made these forces so large that in this particular region, we were able to sort of induce this bend. And sort of that's sort of like the key that you might think about in these processes, that there needs to be some asymmetry, some dependence on, say, time and space that we were able to incorporate here to generate this. If that makes sense, I have, again, this is sort of like, as the forces got, stronger in the middle, we now have a bent shape. And so if this makes sense, you could try playing around with a couple of values of lambda distance, and maybe you can tell me, if I wait here for another minute, on what you'd expect. So instead of changing the lambda distance to 70, maybe you can change it to 30, and then share what sort of like output you get. And the other question then, I guess, related to the previous answer we got, was now, if instead of picking a small region, if you would have not picked those particular X values and sort of tried to change the focal point plasticity plugin uniformly across the tissue, what sort of like behavior would you expect? So maybe you could try quickly changing the lambda distance parameter to 30 in module 7 underscore 3 underscore 2. And if you want, you could change the region parameter as well. So we had in our simulations X between 125 and 225. Maybe you can set it to 0 to 300 or something. Okay, so Ragu has as a parameter has a simulation where they changed it from 70 to 30, and now what you can see is that it's not as invaginated, and you don't see the fold very much. So that's sort of like the strength at which you had changed the focal point plasticity parameter allowed you to give it a better fold in that case. Yeah, that's great. Um, is anybody trying the region parameter, where instead of picking between x at 125 to 225, you're changing it perhaps everywhere? Some values I could suggest. You could do 0 to 300. You could do, yeah, 0 to 350 would be the whole simulation. Or you could remove that line entirely. Yeah, if anybody's trying that, it should be that particular line should be in line number 47 of your module 7 underscore 3 underscore 2, if you want to give it a shot. Um, but if not, I will move on unless there are any other concerns or questions. Okay. So I think the next couple of sort of examples I have will take us deeper um, into the steppable file. And so here's sort of like to motivate you. So we have now a situation where we're able to build an epithelium, put FPP links in it. Um, we're not going to try to mimic this epithelial, slowly sort of like incorporating the FPP parameters along a particular direction. So we are going to go, say, from the left to the right of the tissue. We're slowly going to activate cells at a time, and then we're going to change their FPP parameters very sequentially. And then we're going to see what are some of the patterns that we can get. Eventually, our goal is to sort of being able to mimic pinching of different regions of the epithelium, like you might see in a segmentation process like somitogenesis. Um, Basically, this was what I was interested in. But the goals of being able to have more control over the FPP FPP parameter is probably more universal than just trying to mimic somatogenesis, for example. So I'll go over the tissues and we can talk as we go along. So there's another comment in the chat. Yes. So they're judging from the picture, I think you probably had changed um, target distance, like UD's pointed out, rather than lambda distance. So yeah. So basically, if you set the target distance between the cells to be too high, because of the link strength, they're going to just overcome the contact energies to actually like separate and do what you have. So yeah, but that's great. So now as you play with these parameters, you will know what does what, and how realistic you have to make the FPP parameters in comparison to your whole simulation. Okay, cool. So for this, what we're going to do, and I'm just going to quickly look at how much time I have. So I have broken down this module into two parts. So we have the first part, which needed a little bit more setting up. So I have already set up these steps for you in this module. So feel free to download it and try running it if you'd like. Like I said, the goal might not be that crucial to you, but I can tell you which of the computer properties I'm using here so that if those concepts are more useful to you instead. So what I want to do now is you saw that how we had incorporated regions to change those FPP parameters. Suppose now I want to do it sequentially from left to right, and I want to slowly activate FP parameters in a particular direction. So I want to go from a scenario where initially maybe what I have given permission to one cell to basically start constricting, but its neighboring cell has not gotten that permission yet. But over time, now the cell has the permission to be able to constrict, and now both of these cells can change their FPP properties in order to in order to basically change their cell shapes together. So to achieve this, what I'm going to do is set up a lot of these cell features inside the steppable file. So if you go to module 7 underscore 3 underscore 3A, you should be, and you go to the steppable file, you should be able to see some code that's basically setting up the epithelial cell layers, but now in the steppables, inside the steppables, and you already saw some of that with Julia's modules as well. So the interesting functions that we can use here are something called cell field. So in XML, when you were initializing, say, uniform initializers or the blob initializers, you were putting limits of cell positions in the XML file itself. But using cell field, what you can do is you can create a bus cell and assign the positions to cell field. And so if you check out the steppable file there, you should be able to see a code for this. And so simultaneously, you should remember that if you're setting up things in the steppable, don't forget to delete additional syntax in the XML, or it's going to, you know, override syntax from the XML and the steppable file. And the reason why I'm doing this in the steppable is that so as each apical cell is being initialized, I can add, dictionary attributes to these apical cell types. So I'm choosing two dictionary attributes. One is basically this construct tag that I was showing you that lets me keep tag of whether each cell has permission to do something or not. And then I also have a counter that's basically measuring my left to right direction. So basically, as I'm going through these steps, has that particular, what position is my last activated. So you should be able to also see that. And I have some other steps where, because I want to mimic sort of like a biological tissue, and my beginning is not going to be able to connect to its end. This is some head to tail positioning. So I have fixed boundary conditions, and I'm trying to also like have some sort of like boundary conditions so that my tissue is not is sort of like the ends are not affecting my simulation. So I've tried to make the first and last cells immobile, and you saw how Julio was creating his wall cells there. So it's sort of like a similar idea, where you set their lambda volume to be too high that they're not making any energy changes or calculations. And then we're going to do the same where we have initiated FPP links between the apical compartments. And we are also keeping track of the apical IDs, which is helping me go from left to right. So all of these steps have already been performed in 7 underscore 3 underscore 3A. Feel free to download it. And if you are checking it out and you have questions on any of the CompuCell capabilities as you look at the steppable, please let me know. So this code, 7 underscore 3 underscore 3A, should give us something like this, where now instead of the XML, we have just set up our initial conditions through the steppable file. I have fixed my cells here in my goal, and then I have like put FPP links between them. And now these are the next two goals that I'm trying to achieve. And this is where that example of the two cells that I was showing you comes in. So what I want to do is pick a particular rate of activation because I don't want to do, I don't want to give permission to my cells to change their FPV properties continuously, right? I want to have some speed at which things are propagating across the tissue. So that's my rate of activation. And then what I want to do is if both my cell and its neighbor have been activated, I want to start changing the FPP properties. Does this make sense? Sort of, I don't know if you guys are looking at the code versus this, but do the goals make sense? So we're trying to like have some sort of head to tail changing of properties, and we're going trying to change FPV properties sequentially, but we need to know, left from right. So we are adding additional dictionary elements to make sure we're going up, um, uh, we're going in a particular direction. Does that sound okay? Right. Um, so once we have sort of this, what we're going to what we're going to do now is the next couple of steps, which is like trying to activate things in pairs. So to do this, so these are steps, the rest of the steps. So I have a particular weight, which I've defined as this wave speed over here. And now I'm doing the following. So I have all of my apical cell IDs. I have something that goes from left to right. And every time my condition is met, that this like wave speed is achieved, I am going to turn the tag on for that particular cell to 1. And then this counter just helps me progress in a particular direction from left to right. I'm also adding this because I don't want it to like keep finding cells which do not exist, and also I don't want my last cell to be activated. So this particular tag makes sure that my second last cell in the simulation is the last cell that's going to be activated by by this passing wave. So do you have, um, if you run simulation 7 underscore 3 underscore 3B, this is what you should see. If you wait long enough, everything is going to be activated. But if you watch the simulation, what you should be able to see is that oh, sorry, I think I jumped the gun. Okay, right. So I should point out this is simulation, yeah. So this is just where we are keeping tags, keeping note of the tags. Our next part is where we are going to change our FPP properties. So this is where all the change happens. So now we have we have a part of a code that every time that wave speed condition is being met, we have activated the cell to have a tag of either 1 or 0. If the cell has a tag of 1, then let's look at its neighboring cell, which is this FPP link. That's what it's achieving. So if the neighboring tag also is able to constrict, we can do one more check that we're counting the loop only once, so that if your neighbor cell is to the right of my previous cell, only then run the loop. Otherwise, it's going to check twice. If this condition is met, if both of them have these activated permissions, let's start changing our FPP properties. And now, if you run module 7 underscore 3 underscore 3b, this is what you should see. Like I was saying, if you wait long enough, everything is just going to get activated all at once. But it will look like that everything has gotten activated. But if you watch the simulation in time, you should be able to see that you're starting off with a fairly level epithelium. As as time progresses, things are just starting to like pull on each other, and you are going to see cells basically reorient from left to right. If you can download and run 7 underscore 3 underscore 3b, let me know if you're able to achieve something like that. people are trying versus if you um you could also like do it later, just so I know the pace. So give me a thumbs up if what I said makes sense. Um, oh, great. Thank you. Uh, so that's great to know. Aritra has a simulation that's basically showing the sort of like progression. So if you look at the screenshot in the chat, you should be able to see that cells towards the left look like they're like more closer than cells towards the right. And so this is the way oh, thank you, Raghu. So I'm guessing this is the previous simulation where you had increased. Oh, no, I can see the pixels as well. No. I'm guessing yes. This is the previous simulation where you had increased the limits of x to be covering a larger distance. If that's correct, this looks great. So now you can see that the this is B. Okay. So that is interesting. Okay, so that makes sense. So if your simulation has been running a while, yes, you're not going to really see these differences in your FPP properties because like you have already exhausted your FPP changes to the maximum during the simulation time, and you're not going to see the differences in the anterior posterior properties that we're talking about. But let me quickly show you how we can now exploit this. So we have been able to, sequentially modify focal point plasticity plugins in space and time, and where this could, prove to be useful. So one thing, if you just sort of like notice this, and in the case of this sequential activation is, you're asking these cells to maintain a target distance, but you're not giving them enough time to sort of like, adjust their positions or to meet their target distances because you're increasing these focal point plasticity parameters sequentially. So what's going to happen is that some of these cells in the middle, they are not going to be able to match that constraint. So as that happens, cells in the middle are going to be a little bit more stressed than cells which just got activated by this like wave of progression that's going to, because they have a little bit more space to be able to meet that target distance. So what we're going to do is now we're going to sort of like put a number on this sort of like level of strain that these cells are feeling, and we're going to use it to be able to like break our focal point plasticity links. So our next couple of steps should be in module 7_3_4. So what this is going to do is the following. So, we're back to our step function that we had created as part of module 7_3_3. So what we're going to essentially do is measure this quantity. We're going to ask that for each cell, how further away from your target distance are you at? So just calculate, like, this is, I gave you a target distance to match. How far away from the target distance are you? And you can use sort of like a normal Euclidean distance concept to sort of like measure the distances between those compartments. Note our definition of this strain is also going to include the lambda, because, and this again comes from how you're calculating forces from your energy functions. So this lambda will feature in that force calculation. So our total like amount of strain that you're feeling at the moment is going to be proportional to both the lambda distance and the change in the change from the target distance you're away. And you can like, if you don't want to think about it too much, you can ignore that -2 for now, but that also comes from how we are converting the how we're estimating that strain from the energy function. So together, this gives us a measurement of this strain. And suppose we were to set up a threshold on the strain. I've just set up a number here. So what I'm saying is that if your strain gets too high, so like you're not able to achieve what you were told to achieve, just break that link. And I have appended all the links to be broken to this list, which is self.list.del. And later on, we will be using this property. In the code, you will see that we have this delete FPP link that will loop through all of the links in this list and break them. And so this is the cross of the module where you're like, okay, this is my simulation. I have set up FPP links. I'm activating it sequentially, and I'm asking you to match a target distance at each of these steps. If it gets too much for you, just break that link. And as that happens, what you now should be able to see is that now you're going from a continuous epithelium to regions that are just pinching off by breaking it at certain places. And our simulation is pretty small to begin with. There are just 30 cells that I've put in. You can try increasing the simulation space and then trying to see if that basically gives you a fewer more clusters with more uniformity than what you have here. But this code should be under module 7 underscore 3 underscore 4. So if you run this, you should be able to see basically breaking an epithelium into individual clusters depending on certain features of the focal point plasticity plugin. Are people able to find the simulation and run it? Awesome. Thank you. I'll just wait for maybe another minute and then check if more of you are running it or if there are any questions. Basically, if you have questions related to, you know, initializing styles and steppables, breaks, dictionary modules, feel free to ask about that as well, because this is just a particular example that I'm showing here. Awesome. I have a screenshot, and yeah, you can see sort of like folds in the layer, and you can see the different units nicely. So that's great. Oh, thank you, Kyle. Yeah, that looks great. So yeah, like I was saying, so if you look at these simulations, you get because the simulation size, I think you're right, that looks right. Because the simulation size is small, so these boundary effects from our like last two fixed cells are creeping in. So you might notice, depending on which way these cells go, you might see more variation in the first and the last segment sizes more. So as you increase the simulation, those boundary effects should be minimal. But yeah, thanks guys for the outputs. That's great. And so now you could combine, these tasks with other CompuCell capabilities if you want. So I was very interested in understanding like how, depending on that speed of activation, that wave speed parameter that I showed you, how uniform do these clusters get? What are the parameters that will change it? Basically how fast does lambda have to increase versus that wave speed passing through this tissue? And what are the sizes of these clusters you can get? So one way that you could think about is sort of like visualizing where these cluster breaks occur. And you could combine it with scientific plots to sort of like visualize this line break positions. And if you like visualize where these breaks occur and you calculate, the distances between these regions, that should give you your cluster size and so on. So these are some of the parameters that you could play with. But maybe we could do one last task before we break, which is this one. So if you go to module 7_3_5 and you go to line number 96, so that's where we had set that, strain threshold to 400. Maybe we could try changing it to 250, and then we could see what happens to, what changes from these simulation outputs that we have in the chat. I'll wait for like a minute or two because this is the last stuff, and this was my last slide as well. So just wait to see if you're trying that, and yeah, also please, if you have any questions, happy to answer. Oh, nice! You got the FPP, the visualization to work as well. So that's basically showing you where these cluster breaks were occurring. And this is where we have utilized the other FPP, um, the other dictionary element called counter, because our counter was keeping track of the positions of these apical compartments. So whenever a break occurred, we were able to mark their positions. That's great. Okay, so we have an answer from Aisha that the clusters are tiny now, so that's perfect. So we had so from going from 400 to 250, what we had essentially done was change the threshold of this, strain the cells can endure. So now if the threshold is tiny, the cells are breaking more faster than at 400, and that's why you see more tinier cells. So that's another parameter that you could play with. But yeah, I mean, these are just like I said, like some focal point plasticity parameters and how you can change things in space and time. Like your goals might not be the same as this module, but hope that you have seen this combined with Julia's modules, you get a good flavor of what you can achieve with CompuCell. And with that, I'm going to put up the final slide in. But yeah, if you have any questions on any of the modules, I'm very happy to answer. Yeah, and thank you so much for staying till the end of the day. I'm going to look at an output from Raghu. Yeah, that looks great. So is this could you also type what threshold you set it? Yeah. So now if you increase it to 500, now you can see that the clusters are bigger. And so for the same simulation space, instead of the 4 clusters that you're getting 3, because now the cells can sort of like endure more strain. So those are sort of like that's what that parameter was helping us achieve. And thanks, Hayden, for putting in the final module poll. Yeah, please let us know if this content was helpful to you. We're always looking for ways to make it more useful to the users.
All right. Thank you, Priyom. Everybody could please fill out the poll. It's our last one of today. And if you have any questions about Priyam's session or any of the other sessions today, or any questions more generally, feel free to ask them now. You do not have any questions and you've already filled out the poll, and you are free to go. Enjoy the rest of your evening, and we will see you back here tomorrow for day 8 of the workshop. I have a question from Maisha in the chat. Priyam,
How would you extend this to get something like plume information in the kidney? So actually, like Julio has a very nice simulation of polycyst formation where he has coupled with but I guess he has a polarized model of polycyst formation. If you're interested in more from a cell layer that has already been, that already exists. But if your question is how you're going to model something from a flat layer into a 3D tube, I think you can definitely achieve it. You'd have to extend some of these capabilities to have, start the 3D simulation. You can definitely apply focal point plasticity links between 3D cells as well. And and it's definitely possible to do this, in 3D. Um, can you share the modeling for that, Julia? I don't know if you have the paper handy. Yes, I can. Let me find it out. Uh, Meanwhile, so can we model instabilities like growth-induced tissue wrinkling using this? Absolutely. So you could, yes. So I don't know if you're thinking more from the perspective of like confluent layer of cells, which are growing in a confined space. You can absolutely do that. You can measure sort of like forces, I mean, pressures as these cells grow, which is, I believe, something Gilberto might have talked about. Um, and sort of then if you want, if you need like folding capabilities, you can incorporate that with links. So yeah, you could combine a few things to be able to read pressures, forces inside the growing cells with sort of like fixed boundary conditions to model wrinkling. Yeah, that's a great question.
any other questions? Right. Well, if there aren't any questions, we may go ahead and wrap it up there. Last call on the poll. And we can give people 15 minutes back that we had to take from lunch today. But we will see everybody tomorrow at 10 o'clock. Priyom and Julio, if you want to, in a minute, we'll pop over to James's personal Zoom and have just a quick debriefing if you've got a few minutes.
Could you send me the link to that, Hayden?
Yes. Yeah, well, we move over there. James, are you there?
Be right there. Just let me finish one
Okay.
thing up and I'll head over them.
Yeah, no problem.